we're going to look at variation. This is section 3.7. And variation, it's a way of doing mathematical modeling. So one thing we do is we might look at how to, well, describe some kind of phenomena, some cause and effect, some input-output relationship we might see in the real world. So for example, we have different types of relationships. We have linear, and this is described with lines like y equals mx plus b. So we're looking for relationships we can describe with lines. Now we have polynomials. And this might be something like y is an x to the n a1x plus a0. And we can use polynomials to describe all kinds of things, well, at least within a limited domain. So we can say something like this. It's polynomials give us something like that, but we can usually describe some of the polynomials, say, close in like that. We could do something that's cyclical, and we'll talk about this in trigonometry. So say y equals a sine bx plus c plus d. And we'll get some sine wave that's doing something like this. So we could have something that's cyclical in nature. We have exponential functions, and we'll see these in sections 4.1, section 4.1. And these typically look something like this, or maybe something like this. So again, these are phenomena we see in sort of in the world around us. We can describe using these kinds of models. So we've seen rational functions, and we could also use roots as well. But when we're talking about variation, we're again talking about models. And for the most part, we're going to be dealing with either really a kind of line, a kind of rational function, which we've been studying in this chapter, or a type of polynomial. And we want to go over what some of these look like. Now, what's typically going to happen in this section is going to be asked a question. Y varies somehow with a variable or other variables. So we want to decode what that means. So the first one is y varies directly with x. So what's going on here is that we see x change and we see y change. And typically what's going on, if the absolute value of x increases, we see the absolute value of y increase. And it increases linearly like a line. Likewise, if this decreases, this will also decrease. Excuse me. So what we do when we say y varies directly with x, we're saying that y equals some constant k times x for k greater than 0. When we say y varies directly with x, we always bring out this formula. We're always going to use this. Now, what we're going to typically do is this. We're going to be given some information, x value and a y value. And we use that to solve for k. And then once we solve for k, we're going to use our newly found formula. Now we know what k is. We'll answer some question like, well, if x is this value, what y value do you get? Let me show you with an example. So alligator tails vary directly with body length. And so this is the length of alligator tails is what we're talking about. And they vary directly. So what that means is that we're going to have that formula of direct variation, y equals kx. So now they're going to give us some information. So let's say we have this. If a tail is, and let's see here, 3.6 feet long, when the body is 4 feet long, find the tail length when the body is 6 feet long. So if the tail is 3.6 feet long, when the body is 4 feet long, find the length, and this should be the length of the tail. I don't know if you can see that, that says tail there. We want the tail length when the body is 6 feet long. So how do we go about doing this? We've got to start with this first. We're told that it varies directly. Now we have two variables, the tail and the body. So instead of using y and x, I'm going to use t and b. And the way this is set up, the tail is 3.6 feet long when the body is 4 feet long. So in other words, we get the tail length when we get the body length. In other words, you put in the body length, you produce a tail. So that means this is going to play the role of y. This will play the role of x. So since this is varying directly, y equals kx now becomes t equals kb. All right. Now we're told that we get a tail of 3.6 feet when the body is 4 feet long. So that means a tail of 3.6 feet equals k times a body of 4 feet. So we want to use this information to solve for k. So we just divide both sides by 4. We're going to get k is 0.9. So now that k is 0.9, we have our full formula. T is 0.9 b. Now that we have that formula, now we can finally answer the question. So what kind of tail are we going to get when the body is 6 feet long? So we just take that 6 feet, we plug it in for b. We get a tail of 5.4 feet. And that's our answer. So when we see direct variation, we're always going to have an output variable equals some constant k times the input variable. All right. So that's one kind of variation. The next one. Y varies inversely with x. What this means is we construct a model, a formula, with k over x. When y varied directly, we got a formula that was a line. Now, when it varies inversely, we have a formula that's going to be a rational function. And again, k is going to be greater than 0. All right. So let me do an example with this. Now let's say we have the water temperature. Varies inversely let's see, with depth. So say at 1,000 meters, say this is in the middle of the ocean, the temp that's going to be 4.4 degrees Celsius. So varies inversely tells us what kind of formula we're going to use. Y equals k over x. And then they've given us some information. We have an input of depth and an output of temperature. The idea is that you have to drop down to that temperature, drop down to that depth, and then you'll discover that temperature. So you drop down to the depth first, and then you find the temperature. So that seems to suggest the depth is the input, and the result, the consequence, the output is going to be the temperature. So we have that for us already. Now they're going to ask us something to find. What is the temp? At 5,000 meters. Well, let's say we do this. Let's let D equal depth. And let's let T equal temperature. So again, we're going to use the depth as the input and the T, the temperature, is the output. And so the way this sets up, because this is inversely, we use a model like this. Outputs Y, for us output will be temperature. And then K over the input, depth. So now we need to use the information to find K. And so what they gave us was this. At a depth of 1,000 meters, the temperature is 4.4 degrees Celsius. So that means an output of 4.4 is K over a depth of 1,000. So we solve for K. Multiply both sides by 1,000. We get 4,400 equals K. And so that means our formula is temperature is 4,400 over depth. And that's our formula. Now we can use this to answer the question. What is the temperature at 5,000 meters? So our depth is going to be 5,000 meters. So we use our formula. times 5,000. And we divide that and we get 0.88 degrees Celsius. And that's it. That's our answer. So again, inversely tells us what kind of formula we're going to use, and then we use this information to find that missing constant in that formula. And then once we have the missing constant, we plug in the depth and get the temperature. All right. So another kind of direct variation you'll get is y varies directly as the nth power of x. Now again, this is a direct variation, but we're making a slight change here. We're not going to say y just varies with x. We're going to give x an exponent. So what we get is this. Y equals k x to the n. And again, k greater than 0. Likewise, we could say that y varies inversely with the nth power of x. So what that means we have y equals k over, let me make my k a little more k-like, k over x to the n, and again k greater than 0. So you can have a direct variation with the power of x. You can have inverse variation with the power of x. So let's do an example. So we have this. So sound intensity varies inversely with the square. So square means a power of 2, or n equals 2. It varies inversely with the square of distance from the sound source. So it varies inversely. So this tells us we have an inverse variation with the power of x. In this case, the power is going to be 2. And what being varied inversely here is the distance from the sound source. So if you change seats in a movie theater, so you are twice as far away from the source how does this effect the intensity. So you're sitting in front of a speaker, say. Let's say you're in row 2 and the speaker's in front of row 1, like at row 0. We'll call that location row 0. And you're sitting in row 2. Let's say move from row 2 to row 4. So the distance now between you and the speaker is twice as much as it was from before. Well, what does that do to the intensity? Well, they didn't give us any information on this, so we're going to get sort of a relative answer. So let's take a look. We know this varies inversely. So let's let I be the intensity. And let's let D be the distance. Now D is supposed to be square because we're talking about the square of the distance. And that varies. The intensity varies inversely with the square of this distance. So that means I is K over D because it's inverse variation. But it's not just D, it's the square of D, or that's the power on D, that 2. So the square of D makes it D squared. So inverse variation will give us intensity varies inversely with distance, but it wasn't just distance, it was the square of the distance. So I equals K over D squared. So what we're going to do is this. Let's say we change our distance. Instead of being a distance D away from the speaker, we're now a distance 2D away from the speaker. Now we know when we're a distance D away, that's our intensity. What happens to this intensity when we switch from this to this? Well, what happens? Now the distance is 2D. And remember, whatever that distance is, we're squaring that whole distance. So that twice distance, the whole thing's being squared. So this gives us K over 4D squared. And we can factor out this 4 as a 1/4. We could say this is 1 times K over 4 times D squared. We could break this up like we're breaking up fraction multiplication. And this is the part we want to see. K over D squared is the intensity when we're sitting distance D. Say we're in the second row. That's the intensity. But if we go from the second row to the fourth row, we double that distance. And then we simplify, we find out the intensity, well, it's reduced to a fourth. Now the intensity, our old intensity, is a fourth of what it used to be. So we didn't have to solve for K in this case at all. We could just use symbolics, just symbolism, to come out and figure out that if we double the distance, the intensity will be a fourth of what it used to be originally. So there we go. All right. So next you could have joint variation. So let's say y varies jointly with x and z. Jointly in this case, we make the assumption, though it doesn't say directly, we write it as a direct variation anyway. We call it k, x, z for k, greater than 0. So this will be the formula we're always going to start with. And again, we're going to probably have to solve for k. And the last question, we didn't, but most of these you're always going to be solving for k. So let's say we have this. So kinetic energy varies jointly, this is energy, with, and they throw a little more into this one, mass, and here's the extra bit, the square of velocity. So kinetic energy varies jointly with mass and square of velocity. So if an object of mass 8 grams traveling at, let's see here, 3 centimeters per second has kinetic energy of 36 ergs. Erg is a unit of energy. Typically, you'll see units of energy like British thermal units or BTUs. Probably more commonly in like physics classes or chemistry classes, it'll be measured in joules, Joules. But another way of measuring energy is in ergs. Find kinetic energy for object of mass, and let's see here, 4 grams, traveling at 6 centimeters per second. So the kinetic energy varies jointly with mass and the square of velocity. So we have 2 things to think about. We're varying jointly with mass and square of velocity. So we're going to come up with a velocity variable, we're going to square it. So that means whenever y equals k xz, well, I'm going to say let ke, and this is like capital K, capital E, be kinetic energy. Actually, let's do a different one. Let's call it, let's see, capital Q. We'll go with Q. So let Q equal kinetic energy. And then let M equal mass. And then V equal velocity. Now, the problem says that kinetic energy varies jointly with the mass and the square of the velocity. So that means kinetic energy Q is some constant K times mass times the square of the velocity, V squared. So what we need to do is use information to find K. Now we have some. And there's a mass of 8 grams with a velocity of 3 centimeters per second. we get a kinetic energy of 36 ergs. So that means 36 is constant K times that mass of 8 times, and then the velocity is 3, but we're going to square it. 3 squared. Or we're going to get 36 is K times 8 times 9, or 36 is K times 72. Divide both sides by 72, and we get 1/2 is equal to K. So that means our formula, the one we're going to use to solve this problem, is Q equals 1/2 mv squared. And that is the formula for kinetic energy. So now to answer a question. Mass of 4 grams, velocity of 6 centimeters per second, what's going to be the kinetic energy? So Q is 1/2 4 times 6 squared, where Q is 1/2 4 times 36, and all this comes out to 72 ergs. And that's it. There's one more to mention. And I'm just going to mention what it is. It's what we call combined variation. So with combined variation, you might see something like this. Y varies directly with X and inversely with Z. So we get a directly with X and an inversely with Z. And so the formula we use to set up would be Y equals K X over Z. And again, K greater than 0. And we solve this problem the same way we did with the joint variation. It's just one of the pieces of information will be in a denominator. Well, that's it. If you have any questions, let me know. Other than that, have a wonderful evening.